Hello everyone, let's learn about Dekker's algorithm in this lecture. So Dekker's algorithm provides a software solution to the mutual exclusion problem when there are two processes or threads in the system which are trying to enter into the critical section. Now this is a very important topic if you are trying to prepare for those competitive exams like GET or NET. So trial versions of the algorithm, I've tried to explore each one of them before I move on to the real solutions because each of those trial versions contained one problem or the other. Some didn't guarantee mutual exclusion, one led to deadlock, one led to indefinite postponement. So let's see the versions first. So in the first version, as we can see, there is a shared variable p number which will decide the fate of which process is to enter into the critical section. Now, by default, in this case, the value of p number is initialized to 1. Now that indicates that this is process 1's turn to enter into the critical section. If this had been initialized to 2, it would have meant that this is process 2's turn to enter into the critical section. Now let's start exploring the algorithm. Now, as I said that the value of p number is initialized to 1 first. Next, when we start the processes, let p1 be the first process to start. Now, when it tries to enter into the critical section, first it will need to execute this line of code. That is, it needs to check whose turn is it to enter into the critical section. So it tries, evaluates the condition that if p number equals to 2, that is, it checks if this is process 2's turn to enter into the system. Now by default it was initialized to 1, so this evaluates to false, and now p1 will be executing in the critical section, and after it is done executing in the critical section, it will change the value of the variable p number to 2, indicating now this can be process 2's turn to enter into the critical section. Next it will execute the remaining lines of codes, and finally it will exit. Now let process p2 start while p1 has exited or is executing in the remainder section. So now before process P2 tries to enter into the critical section, it will need to check that if this is process 1's turn to enter into the critical section. Now process P number, this variable P number has been changed to 2 by P1 after it exited from the critical section. So now the value of P number is equals to 2. So this while loop evaluates to false. Now P2 enters into its own critical section, executes, and now it will need to change the value of the p number to 1. Then it will execute in the remainder section, and finally this will also exit. Now let us see that if this solution guarantees mutual exclusion. So let us consider a scenario where process P1 starts with the initial value of P number to be 1. Now, since this while loop will be evaluating to false, P1 enters into the critical section. So for now what we see is the critical section has P1 inside and the value of P number is 1. Now, say at one point of time while P1 is still in the critical section, this process is suspended. Now P2 has started. Now P2 wishes to enter into the critical section. Now the current value of P number is 1 in this case. So when this while loop is executed, this condition will be evaluated to true, and now process P2 needs to wait until this condition becomes false or the value of P number is changed to 2. Now the value of the P number will be changed to 2 only at this step, that is when P1 finishes executing in the critical section, it will come out and change the value of P number. So that guarantees mutual exclusion, like P2 cannot enter into the critical section by any means if P1 is still executing in the critical section. So this solution guarantees mutual exclusion, but this has two drawbacks. One is not so important but anyway significant is, say if you consider this line of code while this while loop. Now in this line of code, the process is utilizing the processor only to check the value of p number, which is essentially a kind of no work condition, and this process is said to be busy waiting. Now busy waiting wastes processor cycle and eventually it leads to lower utilization of the processor, which is not so acceptable in case of single processor system. But this implementation suffers from another very major drawback, where it violates one of the key constraints of implementing mutual exclusion. That is, a process which is not in its critical section cannot affect another process's desire to enter into its own critical section. Now, in this implementation, the value p number is set to 1 by default. So, this means that P1 must enter the critical section first. Now, if P2 tries to enter into the critical section, even when P1 is not in its critical section, since the value of this P number is set to 1, P2 will be stuck at this point. Even when there isn't any process in the critical section, P2 will need to wait. So eventually when P1 executes, it enters into critical section and then sets the value of P number to 2, then only T2 will be able to proceed. Therefore P2 is delayed considerably before it may enter into the critical section. Now the processes also must enter and leave the critical sections in strict alternation. If one process needs to enter the critical section more frequently than the other, the faster process will be made to operate at a speed that of the lower process or the slower process. That is known as a lockstep synchronization problem. Now let us see how this lockstep synchronization problem is tackled in the next version. Now let's see how version 2 tackles the lockstep synchronization problem. Now instead of having one turn variable, that is p number, as we have seen in the version 1, we are using two boolean variables, p1 inside and p2 inside, which indicates which process is executing inside the critical section. Now at the start of the system or at the initialization, both the variables are initialized to false. Now say process P1 is the first process to start and this is also the first process to enter into the critical section. Now before entering into the critical section, it will need to check if P2 is inside the critical section. So it checks the value of this variable P2 inside, which indicates that if P2 is inside the critical section. Now this evaluates to false. Hence, it will move on to this line of code where it will set the value of P1 inside to true. Next, it will execute in the critical section, and finally, this will come out of the critical section and this will set the value of P1 inside to false, and then it will execute the remaining lines of code. Now, for example, if P2 be the first process to enter into the system. So again we consider that the boolean variables P1 inside and P2 inside are set to be false. Now when P2 tries to enter into the critical section, it will first need to check if P1 is inside the critical section at this line of code. Now P1 inside variable has been set to false by default when the system starts. So this will evaluate to false and then it will execute this line of code, that is P2 inside, to be true. Then it executes in the critical section and then after coming out of the critical section, it will set the value of P2 inside to false and then it will execute in the remainder section. Now one thing is guaranteed, that there is no lockstep synchronization in this implementation, because any of the process which needs to enter into the critical section can do so, because instead of one turn variable we are using two boolean variables to make sure that which process needs to be inside the critical section. Now, what might be the problem that is introduced by this implementation? Now, say for example, both the processes at the start of the system, both the processes try to enter into the critical section at the same time. Say, if I give you an example, say P1 starts, so it checks this value that while P2 inside. So since this is the start of the process, P2 inside has been evaluated to false, and this boolean and this while loop will be evaluated to false. And say after executing this step, after executing this while loop, for some reason before it can execute P1 inside equals to true, the processor suspends the operation of P1. Now say P2 is executing. When P2 tries to enter into the critical section, first it needs to evaluate the value of this variable P1 inside. When it evaluates the value of the variable P1 inside, this evaluates to false, because before P1 could complete executing this step, it was suspended. So now P1 inside is evaluated to false. Then it comes to this line of code, P2 inside, and it evaluates this line of code to be true. And after that, it enters into the critical section. So while say P2 is executing in the critical section, say the process gets suspended by the processor, and the processor again resumes this process P1. Now P1 executed till this line while P2 inside. Now this was evaluated to false. Now P1 can safely execute this line of code. Now this executes this line of code, P1 inside equals to true, and next it can enter into the critical section. So what does that mean? Both the processes P1 and P2 are inside their critical section at this point. So this code does not guarantee mutual exclusion. So let's see if the next version that has been implemented, if takes care of this mutual exclusion. Now let's see how this mutual exclusion is guaranteed in this version. Now in this version we have two variables, P1 wants to enter, which is and P2 wants to enter. At the start of the system, both the variables are set to false. Now when we start the process, we do if P1 wants to enter into the critical section, first, before checking if another process is already in the critical section, it will need to set the value of its variable P1 wants to enter to true, which says that okay, now I'm ready to enter into the critical section. Then in the next step, it checks if P2 is already in its critical section. Now at the start of the system, since both the variables have been initialized to false, this will evaluate to false, and P1 can enter into the critical section and evaluate, and then change the value of this variable P1 wants to enter back to false, and then execute the remaining part of the code. Now let us see that how mutual exclusion is guaranteed in this piece of code. Now say for example, P1 starts with both the variables P1 wants to enter and P2 wants to enter being false. So at this point of time, P1 wants to enter is evaluated to true. So it will try to see that if P2 wants to enter has been set to true. So this will evaluate to false, and now let P1 enter into the critical section code. Now let this processor suspend P1 while P1 is still in its critical section. Now process P2 starts. P2 also needs to enter into the critical section. Now this will check, this will first, before checking, will set the value of its variable P2 wants to enter to true. Next it checks that if P1 wants to enter is true. Now in this case, P1 wants to enter has been evaluated, has been set to be true by process P1. So it gets stuck at this point and it needs to wait until the value of this variable changes. The value of this variable will be changed only when P1 will exit the critical section. Then only it will change the value of the variable P1 wants to enter to false, and after that P2 will be able to enter into the critical section. So mutual exclusion is guaranteed in this piece of code. Now, what can be the potential problem that could arise in this kind of a code? So now let's assume another scenario. Now here P1 wants to enter, like P1 starts, P1 executes this line of code, P1 wants to enter equals to true, and this process P1 gets suspended at this point. Okay. Now P2 starts. P2 will first change its the value of its variable P2 wants to enter to true. Now it will move on to check if this variable P1 wants to enter is set. Now in this case, since P1 executed up to this point, so this value of the variable has been set to true. So now P2 waits until the value of this variable changes. Now after some time, P1 is resumed. Now P1 needs to check if the value of this variable P2 wants to enter has been set. Now in our case, the value of this variable is set at this line of code, which has already been executed. Now what happens is that potentially both the processes P1 and P2 are waiting in this step while P2 wants to enter for P1 and while P1 wants to enter for the process P2, and these the values of these two variables will be changed only at these and these lines of codes respectively, which is executed only after the critical section code has been executed, and none of the processes now can enter into their respective critical sections. So this kind of a problem leads to a potential deadlock. There is no lockstep synchronization, but there is a deadlock problem in this version. Now let's see how is it tackled in the next version. To the version 4 and try to find out if the version 4 could do something to break that deadlock. So in this version 4, we again have the same Boolean variables, P1 wants to enter and P2 wants to enter. And now let's see how this has tackled the deadlock situation. Now in this case, before it tries to enter into the critical section or even tries to see that if there is another process in the critical section, it will first change the value of this variable P1 wants to enter to true. Now let us consider the situation as we have seen in the previous version. Let the processor be suspended at this line of code. Now P1 wants to enter has been set to true and this process has been suspended. Now let's start with the process P2. In this case, P2 wants to enter now is set to true because P2 likes to enter into the critical section. Now at this point, it moves on to this checking that if this variable P1 wants to enter is true. Now in our case, P1 wants to enter evaluates to true and hence the while loop also evaluates to true. Now this will enter into this section of code. Inside the while loop, first what happens is P2 wants to enter is set to false. and the process will wait for some time. Now let us assume that at this point of time when the process P2 was waiting for some time out, the process P2 has been suspended. When P2 has been suspended, P1 resumes. So P1 was at this line of code. Now P1 will check the while loop to see if P2 wants to enter has been set to be true. So this evaluates to false because P2 wants to enter has been set to false by P2 after it entered into the while loop. So this while loop entirely evaluates to false. So P1 directly enters into the critical section, and now at the critical section, after it is done, it will change the value of this variable P1 wants to enter to false, and then it will execute in the remainder section. So at this point, say again P2 is resumed, and now P2 changes its value back to P2. P2 changes its value. P2 wants to enter back to true, and then it again tries to evaluate the while loop, and the while loop now evaluates to false because P1 has finished its execution in the critical section. Now P2 enters into the its own critical section and then executes, and then changes the value of this variable P2 wants to enter to false, and then starts executing in the remainder section. So the problem of deadlock is somehow solved in this version. But there is another problem that develops in this version is that of indefinite postponement. Now we cannot make any assumption about the relative speed of asynchronous concurrent processes. We must consider all possible execution sequences. Now the threads could, for example, proceed simultaneously or at the same speed. Now each process can set the flag P1 wants to enter to true, then make the while test in this section. That is, if the other thread is in the critical, other thread or process is in the critical section, then wait for some random amount of time and then again set the flag P1 wants to enter to true. Then repeat the sequence beginning with the while loop. Now as the processes do this, the conditions will remain true, like if this random amount of time that they are waiting be same for both the processes, both the process will see that this variable has been set to true. So this is not exactly a deadlock, but this is known as the indefinite postponement. So in this version, mutual exclusion is guaranteed, no lockstep synchronization or no deadlock is noticed, but we suffer from the indefinite postponement. So this was tackled in the final version of Dekker's algorithm. Now what the final version does is, apart from having these two Boolean variables P1 wants to enter, P2 wants to enter, we introduce another integer variable favored process that or the term value which we had in the version 1. Now let's see what happens in this case. Say we start from the start. So in this case, the int favored process has been set to 1. Boolean P1 wants to enter is set to false, P2 wants to enter is set to false, and P1 is the first process to begin. So P1 wishes to enter into the critical section, so it changes the value of this variable P1 wants to enter to true. Now it needs to evaluate this while loop. Now this while loop says that while P2 wants to enter. Now in our case, this value has been set to false. So this entire while loop evaluates to false. So P1 will omit the entire section, and now it will execute the critical section code. After executing in the critical section, it will change the favored process value to 2. And this P1 wants to enter value will also be changed to false. Now let's see if it does that lockstep synchronization again. Now let us start with this process P2. Now in this case, the in favor process has been set to 1, and P2 likes to enter into the system with these initial values of P1 wants to enter to be false, P2 wants to enter to be false. Now P2 starts. Now first it will change the value of the P2 wants to enter to true. Now it will check if P1 wants to enter. Now this is false according to the initialization of the system. So it will skip the entire while loop and it will directly jump to this section where it will enter into the critical section, execute, and then come out of the critical section. So what we have seen is, even if we have a turn variable, the turn variable does not introduce that lockstep synchronization that we had seen in version number 1. Now let's see how it tackles the indefinite postponement problem. Now say, let's start with P1. So P1 first enters into the system. Now let us consider that this P2 wants to enter is also evaluated to true. Like these two systems start at the same time. Both set their variables. This P1 wants to enter to true and P2 wants to enter to true. Now at this point, while P2 wants to enter, say process 1 executes this step first. Now this will evaluate to true. So now it will enter into this while loop. When it enters into the while loop, it will check that what is the value of this favored process. Now this value of the favored process in this case is 1. Now this if loop will evaluate to false and this if loop will not be executed, and it will keep on checking the value of P2 wants to enter. Now let us come to this process P2. Now P2 evaluates this while loop, and there it sees that P1 wants to enter has been set to true. Now it checks what is the value of this favored process. Now here the value of the favored process is set to be 1. So this if loop evaluates to true. Now it will enter into the if loop and it will need to set the value of the variable P2 wants to enter to false. And it will keep waiting on this while loop where favored process value is still 1. Now let us move back to this process P1. Now what we have seen that this value of this variable P2 wants to enter has been set to false by the process P2. So this while loop will evaluate to false, and then P1 wants to, the process P1 enters into the critical section code. After it comes out of the critical section, this will change the value of the favored process to 2. As soon as it changes the value of the favored process to 2, this while loop will evaluate to false for P2. And next it will break out of this while loop, checking this while loop, and it will set the value of P2 wants to enter to true. After that, when it checks the value of this P1 wants to enter, this will evaluate to false again because P1 has exited its own critical section. So P2 will now come out of this entire while loop, and this will enter into the critical section. And after that, it will again change the value of the favored process to 1. Then P2 wants to enter evaluates to is changed to false, and then it will execute in the remainder section. So this guarantees mutual exclusion while it prevents deadlock and indefinite postponement. So, this goes the final version of the algorithm. So, that is all about Dekker's algorithm. There is no assignment for this particular lecture. I would highly recommend you to take screenshots of the different versions and evaluate it yourself to get a good understanding of how and why mutual exclusion is guaranteed, or the system enters into a lockstep synchronization or a deadlock situation. So that's all for today. If you like the lecture, please give me a thumbs up and share the video with your friends. Thanks for watching.